So just as an overview of what we want to cover here, most industries rely on some type of prototyping, and prototyping has been around for a very long time. Obviously, it's a proven method, but typically you only get to utilize one or two prototypes. You don't have the ability or the money, essentially, to really go through and do 30, 40 prototypes, to recognize or kind of find the best design. So you kind of have to lean on your engineering intuition and kind of some old school knowledge on this would be the best route to go with my design. So what we want to show today is through the use of SOLIDWORKS simulation, we can actually virtually prototype hundreds of different designs with design changes to see which one is the best. I'm not actually going to do 100 today. I'm only going to do 5, but we should see the kind of method of doing this. So the problem set up in what I want to look at here is essentially a front-end suspension component for a remote control car. So this is actually going to be made out of aluminum. And what you see is the two struts that connect in to the top of the bracket. The middle piece there that the two sandwich brackets hold, that's actually what mounts to the top of the chassis. So the design goals for this are to reduce weight. We have to keep our stress below 2200 psi. Yield for this material is around 4000 psi. So it gives us a factor of safety about 1.8. And we're going to rely on about 20 pounds of force from each strut. So we're assuming that the shocks are actually fully collapsed, and this is what we're gaining as far as like a G-force load on impact of the vehicle going over a ramp or hitting a large pothole or something like that. So what I want to do is, and what we're going to start off with is we're going to start off with design 1, which is essentially that plate of aluminum that was just laser burned out. Design 2 has a relief cut to try to reduce weight. Design 3 has a couple ribs put back in, and you're going to see why in a second. As I went through this, design 1 to design 2 to design 3, I saw that the stresses were a little bit high or higher than I wanted. So I added those ribs to try to alleviate that, but it didn't really make a difference, and we're going to discuss why. And then we're ultimately going to end up at design 4, which gives us 10.79 grams. So we're going to start off with 18.6 and get down to 10.79. So as you can see here, just kind of as a spoiler, our stress is still at 2,843, so we're not meeting that original goal, but we did reduce the weight by about 41%. So we're going to discuss what we have, where we're at the end of design 4, and what is our next step. Let's go ahead and go into SOLIDWORKS here, and we can see that this is our assembly model. Now, what I'm going to do is just isolate or do the work on the bracket itself. So let's go ahead and open up this part. And one of the things that I've utilized inside of SOLIDWORKS is configurations. And the nice thing about the configurations are these are linked to our design studies inside a simulation. So essentially what we gain with this is we can do a simulation study per configuration. So if we look, this is where I started, and then went to design 2, design 3, and design 4. So we see the changes from that recess to having the set of ribs and then the full cuts through here. Well, let's just talk about design 1 and what we want to do as far as an analysis. So we can start simulation right from the simulation tab, and I'm going to go ahead and start a new study, and we'll just call this one test, for example. So what you're going to see is the material did come over from inside of SOLIDWORKS. I have a 1060 alloy aluminum assigned to this. For our fixtures, we have to represent the real-life fixturing of this component. And these 3 holes are actually bolted into the chassis via that other component. So I'm going to fix these with a fixed hinge. The other thing that I'm going to do is I'm going to use what is called a roller slider on the back side of the component. Now, typically I would use a split line to kind of show where the bracket actually connects into here, but for first pass we can just assume that this whole back side cannot move in and out. It can only slide along that plane. Our forces we can add directly into these holes essentially via the pins or the strut, and we're going to be dealing with English units, and this is 20 pounds. Now what you're going to notice here is that the forces are always normal to the faces, but what we can do is we can specify in a selected direction. And one of the neat things inside of simulation is if I have a sketch, which is what I use to mount my struts in the assembly, I can say that the force goes along that direction. And we want this to be 20 pounds. So I'm going to add an additional force here. So same force on the opposite side. Select a direction. I'm going to select my other sketch line to give me my proper vector, and we want this to be 20 pounds. So it looks like we're set up. The next step is we're going to discretize this model. So let's hide this sketch here. So we're going to break this down into a series of elements in order to solve our mathematical equations across it. And then let's go ahead and run this analysis and see what we get or we receive from the results. So first thing that I want to do is I want to look at my stress or my results in PSI, and I also want to look at these as far as a true scale. So what we're seeing here is 2,567. So we're not at the 2200 PSI. And I'm going to hide my fixtures and my loads here so we can better see this. And we can also view displacement as well. And again, we can go through and look at this in inches and on a true scale. So we can see our displacement then, if we adjust this to floating, and let's increase this out, is about 0.00024 inches. So very little displacement there. We're really seeing the stress being absorbed in these areas. Now a couple things that we can look at with this is we can evaluate the component as far as we can look at sections of it. So the nice thing about this is typically with physical testing you have a strain gauge located on the part. And if you didn't put the strain gauge in the right location, you may not receive the proper stress calculations or back calculate the stress out properly. One of the nice things with simulation is I look at the section clipping as an MRI into the part. Not only do you receive the surface data that you would gain from your strain gauges, but we can actually see inside of the part through the thickness what our stresses are and how they propagate out into the part. Another thing that I like to look at here is our ISO clipping. And I can basically go in here and say, what is everything that is 2200 and above? So we're seeing these higher areas in these locations. So that's everything above our criteria. We can also do the reverse of that if we need to. Or we can say, you know what, I want to look at this at 1800 and see what that looks like. So the ISO clipping gives us a good view of what we're seeing as well. We can also use what is called the probe tool, so we can go in here and probe at different areas and see what is our stress in our node location. We can plot that out so we can gain data there. We can also save that out to Excel if we need to. Or if I want to know the average, let's say on this face, we can select that entire face, get all of our values. We have a summation, an average, a max, a min, and an RMS for everything on that face. We could also do the body as well, or an edge or a vertice. So what we see here is we're a little bit over our criteria stress-wise, and we're heavy. So next step might be to try to take out weight and see where we fall stress-wise. So what we can do is I can actually duplicate this analysis, and we can call this test 2, and we can pick from our configurations design 2. And what you're going to see is when you duplicate a study, and what makes this very nice, and if I activate this configuration, our forces carried over, our fixtures carried over. All we have to do is simply mesh and rerun. So what you're going to see here is essentially that I did that for Design 1, Design 2, Design 3, and Design 4. Now, how we're viewing this is essentially that we made these design changes without looking at our results. We made all these different versions, and now we're saying, how do they analyze or how do they come out? Well, instead of running these one at a time, what I'm going to do is I'm going to use what we call a batch run, or run all studies. And what we're able to do here is go in and say, run all of these studies and tell us what are the results for each one of those. So what we're seeing is it's actually meshing apart for each one of those configurations, and then it's going to go through and run the analysis for us. And what we see is we have our results. So for Design 2, if we switch to it, we have to activate that configuration. But what we should see here then is our stress is still around 2,534, but we do have that reduced weight. If we switch to Design 3, what we want to look at here is this has the ribs in. We increased the weight here, if you recall, but having those ribs really made no change in the stress. So the stress is really being seen in these areas. And then Design 4, if we activate this configuration, what we're going to see is that our stress actually went up, and the reason being is we actually have this area with too small of a fillet, so that we're seeing essentially a stress concentration here as well. And the reason that we can tell that is obviously because of the visibility there. And if we go into our item here, our legend, we can say show max annotation, and what we're seeing is it's calling it out in this area. So that's our maximum stress. So it's a good indicator of where is the maximum stress, or where was that stress added in if you didn't happen to see that. So another thing that I want to look at is clearly this design is less weight, but our stress is actually higher than when we started. So, what can we do to alleviate this? Well, one of the things that I want to look at is a new type of plot, or a different type of plot, and that plot is a design insight plot. And what this allows us to see is essentially how the force is transferred from the location that is applied to the fixtures. And what we can see is it's actually through this main body and down through the bottom and into that filleted area. So with that being said, I have one more design change that I want to take into consideration here. So I'm going to duplicate my study again, and we're going to switch to Design 5. So with Design 5, I made a couple different changes here. Let me activate this configuration. So with the design insight plot, I saw that the bulk of the load was being applied to this upper area, so I added more mass there. I also saw that we had a stress concentration in that very small filleted area. So this allowed me to make that design change and add a larger radius in that area. So let's go ahead and run this analysis and see what we end up with. And what we're seeing here is we're now right around 2,000 psi, so we're 200 below where we wanted to be. So we're meeting those goals, and if we switch back to our PowerPoint here, what we're going to see is with Design 5, the weight is actually 13.9 grams. So we're meeting our goals, but what can we do to really take the rest of the weight out of this? The next step is really to optimize this part. So what we can do is we can look at this and say, you know what, we can vary the actual overall thickness of the bracket across here, and we can vary the size of the ribs, maybe make those larger or smaller to take out some weight. So we could carry on through the rest of our design process, manually make those changes, add a new configuration, add a new study, run it again, or do a series of batch runs. or we can utilize what is called a design study with optimization. So under Insert, we have a design study. Now, before we even get into that, I want to talk a little bit about sensors. Sensors are something inside of SOLIDWORKS that gives us feedback about our model. They do not have to be simulation related. If I right-click on my sensors folder here, I can add a new sensor. So it can be mass properties, it can sense a dimension, a measurement, or simulation data. We're going to add a sensor here, but we're going to add a sensor for displacement and resultant displacement for the entire model. The other sensors that I added were stress and mass. We want to minimize the mass and we want to keep the stress below 2,200. Now these sensors are what give us feedback in our design study. So let's go ahead and start a new design study. And first thing that we have to do is we have to tell the software what are we going to vary with this. So I can actually pick up on my model dimensions. So my thickness is going to be 0.2. I already have that parameter added. It's as simple as going here and saying add parameter and then choosing on that dimension. I'm going to specify a range for this. My minimum thickness is going to be 0.15. And the reason for this is my overall size is 0.2 thickness, so my maximum is going to be 0.2. But my cut in is 0.125, so I want to still have some meat on this part in that area. My other parameter was the rib, so I want to do a range with the rib, and my initial thickness for the rib is 0.1. I'm going to stick with a maximum of 0.1, and my minimum is going to be 0.05. Now the next thing that we have to tell the software is what is our constraint? What do we have to stay under? So I'm going to tell it my stress needs to be less than 2200 psi. And I'm going to be calling out my Design 5 study. And the reason for this is that's the latest design and that's what we want to stick with. Now my goal is actually to minimize mass. So the mass sensor and the stress sensor are what we're calling out on for constraints as we do this. Next step is merely just to say run, and what we're going to actually see on screen is these dimensions are going to change per these 11 scenarios that it's generating. Now simulation is actually going to be interpolating in between these to find us our true optimal value. Now what you see is as this runs, you're seeing that some of these are coming out as pink or like a salmon color. That means that it actually failed. And what's highlighted is why it failed. So iteration 2 failed because of the overall stress. Same for iteration 4. Iteration 1, 3, and 5 are valid. So those are valid options. The beauty of the optimization is that the software does the work for you. You don't have to take and do any guesswork, any real amount of manipulation or multiple studies. The software comes back and says, you know, within these parameters that you gave me, this is truly the optimal design, which is what we're actually seeing here. So when we select on this, what we're seeing is that my thickness is 0.183 for my overall thickness, so we lowered it from 0.2, and my rib size is just a little bit over 0.5, and we're at 2,148 psi. So that's truly our optimal design. Now my initial weight, sorry to switch to pounds here, what was 0.0288 pounds, our optimal size is 0.0248. If I change my sensor, so if I edit this sensor and we change the mass here, I actually have to update that. And let's do mass. Okay. I apologize. Your evaluate for mass properties here needs to be in units of grams for that to update properly. So we'll go with it here. So this is our optimized design. If I want to, I can actually go into mass properties and say calculate, and our mass in grams is 11.25. So if we go back in to our PowerPoint, we're now down from our original design. So if we go back, design 1 was 18.6, we're now down to 11.25, and we utilize SOLIDWORKS simulation to get there with this optimization study. So the nice thing about this one is utilizing Simulation Professional, we have the optimization option to allow us to go through, give the software a set of parameters. We're not limited to the number of parameters and just tell it to solve and go forward and tell us, what is the true optimal design. The other part of this is simulation alone allows us to do multiple prototypes in the computer very quickly. The overall model for this and the changes that I made took me under a half an hour, and I was able to have 5 or 6 very, very quickly. If I had paid attention to the stress in design 1 and not just done 5 different versions of the model, I would have realized that this upper area needed to be thicker right away, and we might have even gotten down to just 2 or 3 design changes and then the optimization. So all in all, the software really gives us a good feel for what we need and what we need to change to better our designs very efficiently and very cost effectively.